Hi, folks. Uh, Welcome to new chapter number 7 on generation of high voltage in the laboratory, lecture number 1, and in the series, lecture number 25th. In this chapter, we'll be talking about how the test voltages are generated in the laboratory. Test voltages requirement. Why are the test voltages needed? Let's talk about that first. And just a minute. How the test voltages are needed. Uh, yeah, objectives of this chapter is the design features of high voltage AC test equipment. Very typical design features the test equipment have, unlike the actual power equipment. There's a vast difference between a power transformer and between a power transformer and the high voltage test transformer. There's a absolutely difference of day and night. So then there are requirement to produce tuned resonant test set, because the test set otherwise develop the reactive power, because we actually test the capacitance formed by the insulation. We are testing the insulation. Actually, the whole thing, what we have been talking right from the first lecture, it is the electrical insulation base of the power system, which we are talking in this subject. So the electrical insulation, you know that very well, forms capacitance. And so the current drawn by the test transformer is capacitive current, and that is very high order. If you provide in the circuitry of the test transformer, test voltage generator, you can say power frequency we are talking about, some inductance, the capacitive and the inductive current would neutralize, and the total magnitude of the current requirement would reduce, and that is desirable. So that is called tuned resonant test set. Then still there is a requirement for high voltage DC for testing purposes. One requirement is so in some countries, for some equipment, it is mandatory that the test equipment, let it be power cable, let it be transformer, or it be circuit breaker, be tested once again after installation at the site. And how do you test at a remote place with high voltage? There, the DC test sets are required, because with DC testing, no charging current would be there. So the current rating reduces considerably. So the size of the equipment reduces furthermore. So that is what is required. Then we will be talking about high voltage impulse generator, generating both the lightning impulse and the switching impulse, SI and LI. We'll also be talking about high current generator. Current generator. Although this is not high voltage, but we need to generate high current for testing some equipment like circuit breakers. Or if you want to make a short circuit test for a transformer, you need high current generator. We'll be talking about that also. So yeah, why do we test with high voltage? In fact, when we provide an insulation to any equipment, we are supposed to have all knowledge about the behavior of the insulation or the dielectric. And then in the factory, in the manufacturing process, the particular type of insulation is provided in the equipment. There may be number of types of insulations provided in one single equipment. And when, or even during the production, it is desired to ensure the quality of the dielectric provided to the equipment. And that is why every manufacturing factory, every manufacturing of equipment in the factory must possess a well-versed high voltage lab in order to check the quality of electrical insulation provided, not only finally, but also during the process of manufacture. And another very important thing is that all high voltage testing, particularly when we talk about in case of AC power frequency, the testing is always done with single phase AC. So the test voltage generator, AC test voltage generator, should deliver single phase. The equipment, even three-phase equipment, is never tested for all the three phases together. Single phase testing is done one by one for each phases. Why? Because the testing of the insulation provided even in a phase has to be done between the high voltage and the ground. Whenever a short circuit occurs, it will be between the high voltage and the ground. So the testing is also done between high voltage and the ground. So single phase transformers, testing transformers are required. Here is a, as you can see it here, the generation of power frequency high AC voltages. This is one of the biggest in the world transformer producing single transformer producing single phase high voltage to the order of 600 kV. The highest is 750 kV, not 600 kV, but this is 600 kV. You see the human being walking near the this test transformer are so small, and this test transformer is so huge. Why does the test transformer become so huge? Because of the requirement of the volume of insulation needed to be provided in this test transformer. As I mentioned, the current required by such a testing unit would be only the charging current of the capacitor formed by the insulation. And the charging current, you know very well, of a capacitor is very, very small, although it is totally capacitive charging current. So high voltage power frequency test transformers are required to produce single phase very high voltages. Their continuous current ratings are very low, usually 1 ampere. I have seen in the world not more than 3.3 amperes, highest current rating of the test transformer. This is unlike the power transformer, where the current rating and the voltage rating both are very high. So the manufacturing technique of a power transformer and the testing transformers are entirely different. Even 1 ampere is a very large current rating. And this is because high voltage test transformer has to supply only the capacitive charging current to the capacitance formed by the dielectric of the test object. You can further reduce it if you provide in parallel an inductor, or you compensate this capacitive current with inductive current, and that is called resident transformer. You can further reduce it. The more you reduce the current rating of the equipment, you will save on what? You will not save on voltage or insulation. You will save on the conductor cross section, because the conductor cross section of the windings depend upon the current magnitude of the current required by the testing transformer. However, since the voltage rating requirements are high, the test transformers are required to be produced with very high insulation level. And the whole volume, the size of the single unit test transformer, as you see it on this photograph, has increased because of the very high volume of insulation level needed to be provided. Excuse me. This increases the size of the test sets tremendously, and hence single units of test transformers are produced maximum up to 700 or 750 kV single units. You can imagine this is 600 kV or 700 or 750 kV, it will be still bigger. So single units are produced, not larger than that. Recently, larger units have been produced, single units. How? Yeah, as you see in this photograph, this is very typical. Unlike, you just try to compare the two. This transformer and this transformer. This is also a testing transformer, single phase high voltage testing transformer, but of the rating of 1000 kV, not 600 or 700 kV, 1000 kV. This is a recent development. How? You find something different in this. There is, of course, when the transformer is the test voltage is brought out of the transformer. This is the sealed unit of the hermetically sealed container of the transformer, containing SF6 gas as insulator. And SF6 gas insulator at higher pressure works with high high field intensity, and the size of the transformer, it leads to the reduction in size of the transformer windings, etc., and mainly the insulation provided to the winding tremendously. So a very compact unit of SF6 gas testing transformer photograph you are seeing, and of course from the inside of the transformer, the high voltage is brought out with the help of a bushing. As you can see, this is a bushing, and this is again FRP, fiberglass reinforced plastic bushing. So the size of the bushing is also reduced considerably. In this case, for 1000 kV and only zero point 0.6 amperes of current. You would wonder, in this case, this electrode system at which should sustain a voltage of the order of 1000 kV without any partial breakdown, without any corona occurring there. Inside the bushing, there would be SF6 gas or oil insulation, but in the air, 1000 kV, if you do not give, or if you do not extend the size of the electrode, there may be very strong partial breakdown phenomenon there, which is controlled by stress control method we have talked about, by providing very large size of the electrode wherefrom you get the high test voltage. You will see in further photographs of the high voltage test equipment also. Same thing is true, as you can see here also, at the tip of the electrode. Such big dome type electrode is made to be able to sustain 600 kV without any partial breakdown or corona activity there. So this is a newer development of SF6 gas insulated 1000 kV test transformer, which is compared to the conventional paper and oil insulation, as in the previous one. The paper and in this case, the insulation in this tank is of paper and oil insulation. So it makes a lot of bulk or a very large size. Unlike in this case, where compressed SF6 gas at a pressure between 3 to 4 atmospheric is maintained, and that provides a more reliable insulation, hence a compact size of the test transformer. Yeah. Now, it's a problem. As you can see, in this case, 1000 kV, and in other case, limited to 700 kV. How to reduce, or how to, when you want to produce, say 2000 kV, you may need 2000 kV. For example, for testing any equipment with a rating of 800 kV, 800 kV line to line voltage, the testing of single phase winding of 800 kV transformer would be at U0, which is equal to U rated divided by √3 and multiplied by something like 2.5, or some specifications may require 3.0. So this would be, you can make the calculation, that is 2.5 or 3.0 U naught. U naught is the voltage between the phase and the ground. That is U rated voltage divided by √3, that is between phase and the ground, and then multiplied by 2.3 to 3. So you can estimate, you would need a testing transformer of almost about to deliver you a voltage to the tune of 2000 kV. When you need such big testing transformers, how do you produce? I mean, one single unit size would be very, very high. That is why not new, a concept of cascaded power frequency transformer set, test transformer set. Cascaded power frequency test transformer set. What do you mean by cascade? The cascade, a cascade is one after the other, cascaded, one after the other. So instead of producing in one single size the required magnitude of voltage, you produce in steps of 2 or even 3, the steps of 2 to 3 identical units, and in which the ratio of transformation in each unit is common, is the same. The ratio of transformation, as you can see it here, 2 units in this case, you see one unit is this one, and the second unit is this one. So even this first unit is supported on insulator. That means what is happening here, that the primary winding here is acquiring, the container is acquiring the voltage of the primary winding in both, and the transformation ratio is the same. So the container acquires the voltage of the primary winding. That means the container is at high potential, and therefore it must be supported from the ground with the help of insulators. Now, the secondary of this first unit is coming out of the container here. This is the secondary voltage output of the first unit, and that is taken here, as you can see, over these pipe electrode system, and the provided to the second unit as its primary. This is the primary voltage going to the second unit, and the output of the second unit is here. This is the output of the second unit on your left. That is the output voltage of the cascade test set. What is happening here? The transformation ratio being the same, every time the voltage transformed is added in series, you can see. So this is a two-stage AC testing cascade, 1200 kV or 1.2 megavolt, 2 times 600 kV. Each unit here is producing the output voltage 600 kV. So this is the first 600 kV going to the primary of the second unit, again transforming it in the same ratio to give output again of 600. So 600 primary, 600 add and transform, you can say, to double, that is 1200 kV. The transformation ratio, you can say, is 2 times taking place in both the units. Both units are identical, and in both units, the interesting part is that the container acquires the same potential as that of the primary unit, and the secondary unit is taken out with the help of a bushing here to the support to the electrode supported by the ground here. This is the support from the ground of the total or secondary output of the second unit, giving you the 1200 kV. This is giving you 1200 kV. Yeah, the ampere rating here is also very, very small. It is only 1.25 amperes in the current rating is also is again very small, because for testing purpose you don't need very high current. You need only the magnitude of current to be able to provide the charging current formed by the insulation. Yeah, some interesting thing here. Why such big thick pipes are taken for connection here? As I mentioned in the last two pictures, when you have very high voltage and you could connect with a very thin wire, because the maximum current to be carried by the connecting units in the whole system is maximum 1.25 amperes. You could connect with very thin wires, it would sustain the amperage. But what would happen if you had taken a thin wire instead of these thick pipe-like conductors? There would be a very high field intensity around the thin wire, and the thin wire around the thin wire, what would happen? Should know by this time, partial breakdown or corona activity would take place. So all these connections would have had corona activities if you had taken a thin wire instead of these thick these are piped conductors of large radius, and larger is the radius, the Emax reduces, and you can check by the partial breakdown activity by reducing the maximum field intensity around any conductor. So that is also a method of stress control in this case for these connectors in the air carrying high voltage. Let's try to learn, the diagram, with the help of a diagram, a schematic diagram of three transformers, three identical transformers in cascade. The one here is the primary winding, as you see, 1, 2, 3, 4 are as you see it here, one is the primary winding, 2 is the secondary high voltage winding, 2 here is the secondary high voltage winding, this one secondary high voltage winding. The number 3 in all these are all identical transformers, 3 identical transformers connected in a fashion which you must learn. 3 is the tertiary winding. As you can see it here, this is number 3 is the tertiary winding, and fourth The fourth is the core. Number four is the core. Yeah, this is the core of the transformer. So there are three windings: primary, secondary, and tertiary winding, and the core in each case. And each unit has got identical uh, make. Again, here also, as you can see, the uh, uh, output of the first unit is shorted with the tertiary winding. That means the tertiary winding acquires the same potential as the output of the first unit, which becomes primary of the uh, second stage. And the output of the second stage or the second unit would be, if the output of first unit is V, the output of the second unit will be 2V. And then in this case, the because the transformer container, these dotted lines show here, the transformer container. Only the first unit transformer container is at ground potential, but the second unit transformer unit acquires the same voltage as the output of the first stage, so it must be supported over insulators. These are the insulators, and the same thing is true with the last stage of the mm, uh, output. The third unit acquires uh, uh, still more, 3 volts. Sorry, this is the output. This was V, and the output of the second unit is 2V. So the input and the container of the third unit acquires 2V. As you can see it here, it is 2V. And so this requires still more of insulation from the ground, the insulator units, as you can see in the previous case here, insulator units for the second stage. This is 2 stage, that is what we are seeing, the 3 stage. The, the second stage is supported from the ground with taller insulator blocks. These are insulator blocks, just bearing the weight of the transformer. And so the level of insulation to be provided for the third unit is more than that of the second unit. And then when you take out the test voltage, the final test voltage of the order of 3V, 3 times the voltage, uh, output voltage of the first, then the here you may need a conductor, if it is to be applied there, a conductor with much more insulation from the ground to support it in air for drawing out the high voltage here, as in the case of last figure. Yeah, you see this is the output, second stage output. So that the high voltage final output of 1200 kV needs much more insulation from the ground. And so same thing is true here in this case. Suppose this is suppose each unit is for 600 kV. In the output you will get 1800 kV power frequency. So this is how the cascade works. Cascading a number of single identical units makes the advantage that instead of transporting, when you want to take it from the manufacturing unit to a particular lab, instead of transporting very big, huge single unit, you produce it in three single smaller units, and so the transportation is easier, production is easier, and erection of the whole set is also simpler in a particular lab. These all these test sets are installed in laboratory or in open. When they are very large, one doesn't want to invest so much in the indoor laboratory because the cost of the laboratory building itself will be so high. So they are also designed for to work in open air. We'll see some photographs. The cascading principle is illustrated as I have explained to you, and which it can be seen that the output of a stage transformer becomes input for the next stage. So this is the principle that output of a transformer becomes the input to the single stage, and even the container acquire the potential of the primary, so they need to be lifted up, supported on insulators. So this is a very common practice for producing very high test voltages in the laboratory. Yeah, I think uh, we are uh, yeah, we have a few minutes more. I can show you something more here. Uh, the high voltage supply is connected to the primary winding one of the transformer one, designed for high voltage output of say V voltage. The other two transformers too are connected in the same fashion, are also designed in the with the same ratio and identical. That is another advantage, that you design and produce smaller identical units. The excitation winding 3 of transformer 1 supplies the primary voltage for the second transformer unit. Both windings are dimensioned for the same low voltage, and the potential gain is fixed to the same value V. The high voltage or secondary windings number 2 of both units are connected in series, so that a voltage 2V is produced at the output of the second unit, as I showed you. The unit 3 is added in the same way. As you can have once again a look at it, the what I just now read out, the windings are connected in such a way which I explained. Then uh, yeah, I have covered every point what is written here. One more photograph we will see. For voltages higher than about 600 kV, the cascade of such transformers is a big advantage. The weight and the size of the testing set is subdivided into single units of smaller size and lower weight. The transportation and erection of the test set in cascade becomes simpler. However, there is an advantage that the primary winding of the lower stage are more heavily loaded with higher current in such set. Yeah, we did not talk about the power units. See, the input power here is 3P, let's say. So what happens here? Uh, there is P output. Output of the first stage, power rating is P, and 2 power rating goes to the tertiary winding, which becomes the input for the second stage. So here it is 2 power unit. Again, it is output is divided into P and P. So you have 2 power rating output here, and 1 is the primary input. This P is input for the third stage. So what happens that you get 3 power input, 3 power output here. Here, power. So what is changing here? The voltage has increased from V to 3V, and the power is 3P. What is changing here? P is equal to VI. So the current rating in the first stage is higher. The current rating in the last stage is 1/3 of the first stage. So P remains, V increases. That is the thing. The output current would be smaller as compared to the input current. So the current rating changes in the 3 stages, but the voltage rating also changes. Voltage increases, the current keeps reducing in the 3 units. In fact, the total current required is so small that the conductor size need not be changed for each unit. They can continue to be of the same cross section. The total current required, because the output current, as we learned, is 1 ampere or even less than that. So the conductor cross sectional area in all the 3 can remain the same in spite of reduction in the current being carried by the third stage, and in spite of current being carried in the first stage to be higher. But the insulation ratio, the transformation of voltage ratio is the same. So the insulation provided in the 3 stages remains the same. Get the point? The insulation between the primary and the secondary difference in voltage will be the insulation provided will be proportional to the transformation voltage ratio. So since that is the same in all the 3 units, the level of insulation provided will be the same. And in such cases, it is the level of insulation which increases the size of the units. So that is remaining constant. So the identical units can be produced and cascaded to get higher voltage at the desired current. Yeah, there is another test set here, schematic of here. This is the one of the highest in the world, 2250, 2250. That means 750 kV each unit set here. So as you can see here, the windings in this particular case, there is one more winding introduced, which is known as balancing winding. The circuit has third winding known as balancing winding that is used for balancing the voltage output voltages. These windings are designed to acquire intermediate potentials between two stages. And in the circuit, the transformers of the in the circuit, the transformers of the upper stages have their excitation winding arranged over the high voltage windings of the transformer of the lower potential. I mean, the core, the all the windings are around the core and the over the one another, over one other windings are placed. I mean, this is another way of producing cascaded transformers. And to here, as you can see, 2250 kV, very output voltage of the last stage, and very high voltage requiring very high insulator blocks from the ground. So this is the, as you can see here, the only ground potential is that of the core. Sorry, the ground potential is of the low voltage winding, the lower end of the low voltage winding, and the high voltage winding of the primary of the first stage are at ground, and then they acquire the high potential. The even the container acquires the high potential, so everything is lifted up above the ground. Yeah, the most interesting figure you would find, this is like a huge block, as you can see it here. This is the actual photograph of the test set of 2250 kV, 3 times 750 kV, cascaded and installed outdoors, as I said, because the size of the equipment for to be able to produce 2250 kV is so large that to install it indoors would be a very costly affair to make the building such huge building. So they are often installed outdoors and they must withstand all the weather conditions and in open air. And as you can see it here, this is where are the three units. So this is here is the first unit, and second unit is behind here, and the third unit is here. Third unit is here. So these are the three stages connected in the same fashion as I had explained the two-stage indoor cascade in the same fashion. And as you go up, the voltage is increasing. You would also appreciate that the dimension of the pipe connection here also increases as you go up. As you go up, this is bigger and this is also quite big, so far away. So the dimension of the connecting pipes also increases because they are carrying more of voltage. In the first stage 750 kV, in the second stage it will be 1500 kV, and in the third stage at the top it is 2250 kV. And the human being you can see on the ground. So the uh, whole cascaded test set for 2250 kV AC power frequency generator looks like a giant on the ground. So this is what is very typical of high voltage test AC test voltage generation techniques are acquired. And you can imagine if you need 2250 kV to be produced, that will be good enough for voltages like 1100 kV. Such huge test sets would be required. In our country, we have 800 kV, so even three-stage 600 kV would be sufficient. 2250 kV would be required when you go for 1100 kV system of rated voltages. So let's call it a day. We'll see uh, tomorrow. I can continue